So number 20, according to mastering. And it starts off with this disk that has an axis that is like right along the edge here. Something like that. And I think we are to assume that the center of mass is at the middle. Now, I don't know what the problem is going to ask. I know that if this were on the AP exam, and problems like this are on the AP exam, there's a variety of things they are going to ask, such as what is the angular speed when it reaches its lowest position? What is the acceleration right here when it is released? What is the speed of the edge of the disk as it passes through its lowest position? Those tend to be the kind of questions that come from these, and they are all over the exam. I can probably just reach into the exam, pull out any year, and there'll be questions like this that deal with the angular motion of an object, especially one like this that's got an offset axis. In fact, there are years where they don't put it so conveniently at one edge. They might not tell you where the axis is. They just indicate that you need to find the axis that will provide maybe the fastest speed for it to go, or an expression for the speed in terms of where the axis happens to be. So these kinds of problems are pretty ubiquitous. The fact that there is some numbers given here, I'm going to, I think, proceed without the numbers at all, since not all of our numbers are the same. And that way, when we're done, you can put in whatever numbers you feel like it. So let's say that the disk has a mass of, let's go with M, I think is probably a good place to go. M for the mass of the disk. And you want me to use the radius of the disk or the diameter of the disk? I'm not sure it matters. To me, does it matter to you? It does matter? All right, so want radius or diameter? All right, so I'm going to use the radius. I'm going to start off by suggesting that the object is experiencing an unbalanced torque, and that torque is due to a force that acts right here of amount mg. And the torque arm length is going to be this perpendicular right here, which is also capital R. So before, I don't even know what the question is going to ask. I don't really care. The torque on the disk is going to be R times mg times the sine of 90 degrees right now. It's not going to stay that. The moment the disk begins to move, the angle between the weight and the torque arm is going to change. So I'll point out that in this particular case, the object is going to swing downwards, but in this moment, this exact moment, we could calculate the acceleration. It's going to be harder to calculate it as it moves. The acceleration is going to be a different number all the time. It starts out right now at a maximum. When it is straight down, the acceleration will be 0. Because when it's straight down, the disk will be down here, and the force on it will be straight down. So the angle between the torque arm and the weight will now be 180 degrees. The sine of that is 0. So we have the maximum torque here. I'm saying that because that's a multiple choice question. Where in the object's motion is the torque a maximum? And where is the speed a maximum? The speed's going to be a maximum at the bottom, but the torque is a maximum now. And whenever the torque is a maximum, the acceleration is a maximum. Because the net torque equals I alpha. So if my next step is to find alpha, which it could be, I don't know, I'm not reading the question, then I would proceed from here and recognize that my torque, Rmg, has to be equal to I times alpha. Now, I'm leaving a big set of parentheses there because I don't know what the moment of inertia is. This object is not being rotated about its center. Pay attention to that. Be aware. Whenever we're not using the center, you're going to either have to find the moment of inertia by integrating, or you're going to have to use a known shape and move the axis using the parallel axis theorem. And it's not always the same depending on the year and the problem. This particular example, we can use the parallel axis theorem by using the moment of inertia of a disk plus mr squared. It's r squared this time because we're moving it one radius away from the center. That's going to be 1/2 mr squared, the moment of inertia of a disk, which I am sure you have all memorized by now, plus mr squared times alpha. All of this still has to equal rmg. So if I'm asked to find alpha, and I think I am, I think that's what the question is, what is the magnitude of the cylinder's initial angular acceleration? So that's this. I'm going to solve for alpha, which means getting 3/2 mr squared alpha on this side and rmg on that side. Looking closely at this, I hope you all agree with me that the m's cancel and one of the r's cancels. So my value for alpha is going to be 2/3, looks like g over r. Questions? All right. Well, if I was writing a question, then the next thing I would ask is how fast is it going when it reaches the lowest point in its motion? So in order to consider that, let me draw this a little bit smaller. I have the cylinder here, and it's rotating about this point. It's going to spin downwards so that after a moment, I'm going to have the cylinder there. Now with some angular velocity about the pivot point. Now, this one might not be obvious, but the center of mass changed height. You can't use a motion equation to solve for this. If you tried, you're going to get the incorrect answer because it does not have a constant acceleration. Acceleration is always changing, as I explained. It does, however, change height, and with no external force acting on the system. I want to be very careful here. There is a force that acts on the system, holds the object in place, allows it to fall. Does that force cause an external torque on the system? Now, that's a hard question to know. This object is experiencing an external force. Because of that, it's not obvious that the kinetic energy is going to be related to the potential energy. In fact, I don't think it will be. There's an external force. The pivot holds on to it. The pivot point keeps it from falling. So because the pivot keeps it from falling, the object is rooted in place. However, the pivot applies a force at the pivot, so there is no external torque on the system. So rotational kinetic energy will be related to potential energy. It's a big difference there. The object's not falling, but its center of mass does drop below the position it's at now. So because the center of mass drops below the position it has now, it does lose gravitational potential energy. It doesn't go into kinetic energy directly because there's an external force keeping the disk from falling. It does, however, not cause an external torque, so we do get conservation of mechanical energy in the form of rotational kinetic energy. So we can say that mgh is going to be equal to 1/2 I omega squared. What's h going to be in this case? What should I use for h?
R.
Yeah, 1 radius. The radius was here to the center of mass, and then when it swings downwards, that radius is here. So in this case, it's mgr. I don't think that's obvious for a lot of people. I'd like you to make it so. Write yourself something in your notes. This stuff is all over the exam. It's usually a rigid bar, but it can be a rigid disc like this. That's going to equal 1/2 times, we've already done this, 3/2 mr squared times omega squared. So I can again cancel out the m's, and I can cancel out one of the r's. That's still going to work out. In this case, I get 1/2 times 3/2, so it's going to be 3/4. But when I move it around, I'll get 4g over 3r equals omega squared. So omega is going to be the square root of 4g over 3r. Again, I'm sure you have numbers that they gave you, but... Now, often in these questions, there's a next part where they'll have collisions or something, or they might ask about how fast this point on the edge is moving, something like that. But I think the problem in your homework ends the problem here. When you're looking at a problem like this, you should expect the following questions. They should ask you things like, what is the acceleration of the system when it's first released? If you're asked that, it's an acceleration question. You're limited on your options there. So be aware you have 2 options. It can be alpha for the pulley or A for one of the boxes. But be aware your options are limited in this problem. Net force will solve this problem. There's no doubt in my mind you can use net force in this question. It's probably the hardest way to solve this problem, but it'll work. You would find the net force on the system. The entire system probably is accelerating at the same rate or at a related rate. Again, the entire system is probably accelerating at the same rate. They're all connected. So the 4 kilogram box can't move downwards without the 2 kilogram box moving upwards. So I would expect that it's all kind of connected there. On the other hand, you could use energy to solve this. There's a very clear change in height. One box gets lower, the other box moves upwards. The problem is that energy can't tell you acceleration. Energy could tell you velocity. Force can't tell you velocity, it can tell you acceleration. So they're going to give you different pieces of information. And by the way, I'm giving you the little bits and pieces you're going to need for your flowchart. These are the types of things you look for in the question. A connected problem with a clear Atwood machine can always be solved by force. If you see an Atwood machine, consider using net force. Yeah, that's a yes or no question. Is it an Atwood machine? If yes, you have 2 options. If they want the acceleration, it's force. If they want velocity, it's energy. It's energy because there's a clear change in height. I have an object that acted on by gravity and its height changed. That's energy right there. Now, the next question you should probably ask yourself, and this one's important, is will this object have a constant acceleration? Are the parameters in the problem going to stay the same so that the acceleration stays the same the whole time? In this problem, the answer is yes. There's not a change in torque. It's not like the angle between the torque arm and the force is going to change. The reason that's important is although this comes from force and velocity or omega could come from energy, they are related by kinematics. So you could pick the thing that you like the best to solve this problem with. And no matter what they ask, you could probably get to the answer. So if they ask for acceleration, but you don't want to do force, you like energy better, well, by all means do energy. you can use kinematics to get acceleration. If, on the other hand, you're good at the force stuff, but the energy stuff eludes you, well, get the acceleration, then use a kinematics equation to find the velocity. The reason why I think energy is the way to go is because they tell me it's 1 meter above the ground. That's displacement. They are telling me the height, the change in height of the two objects. I haven't even read the question. I saw that picture and knew that was the right question to assign to you. So let me see what the question actually says. If the blocks are released, how long does it take the 4 kilogram block to reach the floor? All right, so it didn't ask any of the things I said. Time. Time shows up in 3 places in physics for you guys. Kinematics, angular impulse, and linear impulse. Those are the only 3 places that you have seen time. But only in one of those is time related to displacement, and that's kinematics. It's the only place. You are stuck. This is a kinematics question. The problem with this as a kinematics question is that if I start looking at the kinematics of this question, I start trying to figure out, the 4 kilogram box. The 4 kilogram box is going to descend 1 meter. The 4 kilogram box is going to descend 1 meter. That's it. It starts from rest, perhaps. That's probably something I know, but I know nothing else. So if I want to figure out the time, I need either the acceleration of the box or the final velocity of the box. So it looks like it's up to me to decide which way to solve this problem. Forces, because Melissa asked. So when I look at forces, I have to look at each object individually. I see 2 torques act on the pulley. I see 2 forces act on the 2 kilogram mass and 2 forces act on the 4 kilogram mass. Assuming the pulley has mass, and I haven't read the question, does the pulley have mass? Then the tension on this side I'll call T2, and the tension on this side I'll call T1. They are not the same. I know they can't be the same because the tension on the pulley has to be unbalanced in order for it to accelerate. So I know that T2 has to be greater than T1. Do you know those things? Because otherwise, you should be writing it down. So, I'm sorry. Here we go. The one thing that I want to remind you about in these questions, the acceleration is the same for all the objects. That's the thing. So the net force on the 4 kilogram box is going to equal 4 times A. The net force on the 2 kilogram box is going to equal 2 times A. And can't say it the same way here. The net torque on the wheel, the pulley, is going to be I times, A over R. I'm not going to bother putting alpha there. They're all related. I can cut to the chase a little bit and at least, recognize that there's going to be an A in all of these. I need A. Now, this tells me there's going to be 3 equations and 3 unknowns, and I'm going to have to eliminate 2 of those unknowns because every force equation creates an equation. I know that sounded redundant. Every net force creates an equation, so that's 3 equations. What's going to link them all together is the tensions. And the only one of these that has both tensions in it is this one, which means I am substituting into that equation because it has both tensions in it. This side is just going to have, 4 times 10 minus T2 equals 4A. Right? It's got T2 in it. This one's going to have T1 minus 2 times 10 equals 2A. I can skip over the mg stuff, right? We're past that, I hope. Is this an AP Physics 1? But I got to deal with the torque now. This one might be harder, but I am going to try and cut a few steps here. I have made an obvious decision. I don't know if it's obvious to all of you, but I've made this way positive on that side, this way positive on this side, which means I have to make this direction of spin positive. So that positive is consistent all around. Now, with that, I'm going to go up here and deal with my torque equation. On this side, I've got a torque that's going to be, well, T2 times R, and it's positive. On this side, I've got T1 times R, and it's negative. Those are the two torques that act on the wheel. Yep.
Can we assume that the axle's at the center so that the frictional torque that they mentioned, like, you wouldn't count?
No, if there's a frictional torque, I'm going to have to include it. There's a frictional torque? Wow, I probably should have read the problem. What do you think the frictional torque is going to do? Make the system go faster or make it go slower? So when I put all the parts together here, I'm going to have T2 times R minus T1 times R, and they say it's a torque, a frictional torque. So I'm just going to write that as minus torque with a little f here to tell me it's a frictional torque. It's already a torque. I don't need a torque arm. If they told me that I have a frictional torque, then it's just a torque. It's probably in the units of torque if they gave me numbers, right? Is it a meter Newton? So I don't have to worry about where it acts. It probably acts in the bearings, probably acts right in the middle. You know, but it doesn't matter how much it is. Whatever that number is, I'm going to use it. I assume this is a known quantity, though, right? Yeah. All right. So that's how it would go. If that was your question, then we're probably done with that part, but we'll keep going. Is it a solid disk, or they give me a moment of inertia?
Yes.
I treat it like a disk. So what's its mass? What's that? 3. Does everybody have 3 kilograms for the mass of the disk?
No, that's 2.8. That's so close.
It's 3. All right? I'm doing 3. Whatever yours is, you play at home. Let's see, can I... Oh, I'm sorry. I hit something on my thing, and now I'm all screwed. Because everything is bad. All right, I'm going to try and squeeze this in here, but it's going to be R squared. And I'm sorry to do this, but I can't write over on that edge of the board, so I got to put A over R right up in there. And I can't. It goes right there. Sorry, dudes. I could probably do this. Oh, yeah, that'll work. Nope, not so much. All right, so let me just clean up the math. All the R's cancel. T2 minus T1 minus torque divided by R equals 1/2 times 3, you said, times A. I just divided out the R, got rid of it. But it doesn't get rid of because I have this frictional torque. Now, the next step is to figure out T1 and T2 and substitute it in here. So T2 is going to equal 40 minus 4A. And T1 is going to equal 20 plus 2A. Yep.
Where did the T over R come from?
There's an R squared there. That canceled one of the R's in the denominator for the A, which left an R, so I divided both sides by R. That got rid of this R and this R, but this term didn't have an R in it, so I have to put an R in the denominator. That okay? Now I have inundated this board with too much stuff, so let's go to another page. By the way, energy, one equation, just so you know. T2 is 40 minus 4a. That's what I said.
You said T1 was
You've got the answer to your question, right? How long it takes to reach the ground? But this is a tough question. It's long. So let's see. That was 40 minus 4a for T1, right? 40 minus 4a? Minus T2, so minus 20 plus 2a. T2 and T1, there. Minus whatever that friction garbage is, equals 1/2 times 3 times a. It's getting better. I have 40 minus 20, so that's 20. I have negative 4a minus 2a, so that's minus 6a. I have the frictional torque divided by r equals 1.5a. I'm doing algebra, so I feel like I can do this faster. So 20 minus... All right, we're done here. I bet everybody has a different frictional torque and maybe even a different radius. I don't know if any of that's true or not. My numbers are 0.45 for the frictional torque, and the radius has a diameter of 17 centimeters. So do you all have different numbers in that? Yeah. Fantastic. So 20 minus 0.45 for me divided by half of 17, which is 8.5, then converted to meters, so 0.085. Those are my numbers. And that equals 7.5a. Guys, that's just a travesty of justice. That's a lot of work to get A. You know the problem? Doing the energy one might have been faster. It's one equation, but you would have had to figure out a way of representing the frictional torque there. You would have had to do the work done by friction. I'm not sure if that's easier or harder, but you would have had to do that. I mean, at this point, though, finding A is just numerical. Punching buttons is not very interesting. And once you have, it's a long question. I'm sure somebody in fourth period is going to ask about this question. And when they do, I'm going to do it in terms of energy and just tell them that the one in terms of force is here. So if you wanted to see it in terms of energy, I'll make sure it gets. So on my problem, I have numbers and stuff. I don't care about the numbers. Let's focus on what the problem is about. The problem has the car located at the edge of the track, a radius away from the center. And the car is given some tangential velocity. The car is going to roll along the track. Now, the thing is hanging. So the moment I turn the car on, there is a force on the car from the track. It's friction. But there's a force on the track from the car. So the track is going to begin to rotate this direction. Our job is to figure out how fast. But what is the angular momentum of the system before you turn the car on? I'm sorry, what was the angular momentum of the system before you put the car on?
0.
It's got to be 0. So afterwards, the car has angular momentum. I'm going to use a lowercase l. And the track has angular momentum. So this is the car. This is the track. I know you have to leave, but I would say that this might be easiest to do this by treating them both in terms of a rigid object where the car's a point mass with moment of inertia mr squared and linear velocity v over r. I think you might find that to be a good way to go to figure out what the omega for the track is. Okay, so x is measured from the center. Great. Let's see what they ask. Question A, what are the units of C? Oh, that's pretty straightforward. The units of lambda have to be mass per unit length. And I have something times length squared. So I'm thinking C has got to be mass per cubic meter, or mass per cubic length. That one's pretty easy. Let's see what part B is. Find the expression for C. I like that one better. I like that one. Because the mass has got to be the integral of dm. Did you know that? If you add up every piece of mass, that should give you the mass of the object. And we know that the object's density is changing, starting at apparently 0 at the center and getting heavier towards the edge. For example, this piece right here, which I'll call dm, has a mass that is less than, say, this piece right here, which also has mass dm. I'm just going to talk to the iPad. It's the only thing listening anyways. So every dm is a different mass. And I only have to worry about one side of this because the other side is exactly the same. So for right now, I'm just going to say that I'm going to go from 0 to L over 2 and then multiply the whole thing by 2. But herein lies the problem. Can't integrate that. Those limits are based on x. Those limits aren't based on m. So I need to find a way of writing m in terms of x. And that part's not too hard. If you've paid attention at all, you know that I'm trying to find a way to describe this object geometrically. And the easiest way to do that is to immediately change dm into terms of something about position. And they've already told me what to do. They've given me the linear density. In fact, they've said that the linear density is a function. So what I'm going to do is I'm going to assume that every one of these pieces is dx wide. dx wide. That's a small bit of distance. And I'm going to multiply dx times lambda because that should give me how much the mass of each piece is. They gave me mass per unit length, kind of shoved it in my face, I might add, by repeating its units and all that garbage. So they clearly want me to know that this is the mass per unit length. So if I break this thing up into a bunch of pieces, each one of length dx, as long as I know where each piece is, I can take the value of dx and multiply by lambda and tell you what its mass is. So that's what dm will be. It is how big each piece is in length multiplied by lambda. So that part's pretty straightforward. I can write this now as 2 times 0 to L over 2 lambda dx. Now, for those of you who don't know, lambda is just a general Greek character given to linear density. We have several different characters that are kind of reserved for density. Lambda is linear density. Sigma is areal density. That's the mass per unit area. And rho is volumetric density, mass per unit volume. So rho is what should have been used when you're in chemistry, but they probably didn't. They probably just used like D for density. But in physics, we tend to use those 3 terms for different types of density. Either way, I'm going to go ahead and do a little bit of substitution here. 2 times the integral from L over 2 from 0 to L over 2 of cx squared dx. I've built an integral, the solution of which should give me the mass of the bar, which I've been told to use capital M. By the way, I'm pretty sure that C will have in its answer the mass of the bar and the length of the bar. Kind of had to. Yes, sir.
Can you explain the lambda times dx equals dm again?
Sure. Lambda is mass per unit length right? So, and those aren't the, let me write this different just so that I don't confuse you. Mass per unit length. So what I've done is I've considered that this piece is length dx. It's a small, I'm using x as a general term here, but also a term that's already been applied to the problem. That's why I'm using it. I went out a distance x to find this piece of mass, and then I'm saying that if I go out just a little bit further, that little bit further would encompass a small piece of the object. I'm calling that small piece dx. Now that is just the length of that piece. But I'm told that the mass per unit length of each piece is this function. So if I take that function and multiply by the length, that should give me the mass. Because I have the mass per unit length. So dx represents that length. dm represents the mass at that location. So that's why I can do that substitution. I'm taking lambda dx, which is a mass. It's density times length, and replacing it for the mass that's there. Does that make sense?
Yeah.
I want you to imagine that if you have a meter stick, every dx is a centimeter on that meter stick. But every centimeter on a meter stick has a different mass. So lambda tells me how much each centimeter's mass is on the meter stick. Does that make sense?
Yeah.
Okay. So I think we're kind of done here. There's not a whole lot left to do except to do the integral. The integral is with respect to x. So the c can be brought out of the integral, and I'm left with just the integral from 0 to L over 2 of x squared dx. I think all of you know that this is just going to be 1/3 x cubed evaluated from 0 to L over 2. So this is going to give me I don't know why I put 27 there. Guess I was cubing the wrong thing. Is that it? I think that's it. Now it's way down there at the bottom, but I think we can kind of clean this up. M equals, let's see, that'll be, cancel out one of the 2's and the 8, that'll be 4, so that'll be L cubed over 12 times C. So C's got to be 12M over L cubed. Interesting. It does work out to be mass over length cubed. Now, I can't imagine that the next step in this isn't to find the moment of inertia of the system. So I think we're going to do that next. Whether it is or isn't, that's what I would want you to be able to do next. So we've done all of the heavy lifting already to do that. Just so you know, everything we've done here would be required to calculate the moment of inertia. The only difference is that instead of this being our kind of our starting point to find mass, which is what it was, we're going to need to, to find moment of inertia. Give me just 1 second. Just want to kind of start fresh here. To find moment of inertia, we're going to use all the same information. We're still going to use that lambda is cx squared. We're still going to use that dm equals cx squared times dx. But now the moment of inertia is defined as r squared dm. We're still taking every piece of mass, but this time we have to multiply by how far away it is from the axis of rotation and square that, and then multiply by how much mass there is at that point. So it's a similar kind of integral, except it's a weighted integral, where the weighting of the integral is heavily shifted towards where the mass is versus how much mass there is. So for this one, I do want to point out that the R is a placeholder. It's a placeholder that's left over from the generic equation for moment of inertia. It represents the shortest distance from the piece of mass to the axis of rotation, which in this problem will be x squared. dm is still represented the same. To figure out how much mass is at a specific location, I need to find out what that location is and then use that with the density to figure out the mass. So my next step will be to put in x squared times cx squared dx, because that's what dm is. Now, granted, I'm still going to do from 0 to L over 2, but you could do this from negative L over 2 to positive L over 2. That's the way the book would like you to do it. They're real big on those Cartesian coordinates and all that garbage. I'm just not going to do it that way. I'm just going to put a 2 out front and know that moment of inertia is not a vector quantity. So I can figure out just what the moment is for half of it and then double it. All right, well, that's really about it here. I do need to remember that C is 12m over L cubed, because I want to make sure I get that in the end there. So the C pops out of this, and I get 24m over L cubed, the integral from 0 to L over 2, x cubed dx. Right, x squared times x squared is x to the 4th. Oops. Thank you, Hannah, for making that face. It allows me to know that somebody's paying attention. Other people might have been making that face, but I'm not wearing my glasses. Not a whole lot left, but I guess I'll do the rest of it. So I'm thinking 24m over L cubed, 1/5 x to the 5th, evaluated from 0 to L over 2. And I forgot the 2 out front, so let me throw the 2 out front there. And I had the 2 out front. I multiplied by 2. All right, so this is a mess. 24m over L cubed times 1/5 L to the 5th over 2 to the 5th. Is that 64? 32. What was I thinking, 64? That's just ludicrous. Not a whole lot here, except I got a fraction to deal with. 24 and 32, though, both have 8 in it, so I can make that 3, and I can make that 4. And so I get what looks like 3/20 ml squared. I am not surprised by the ml squared. Now, a uniform bar rotated about its center is 1/12 ml squared. Does this answer make some sense compared to that? Would I expect the moment of inertia of this bar to be bigger? And the answer is yes. More of the weight is shifted towards the edges. So I'm glad that 3/20 is bigger. I'm sorry, 3/20 is bigger than 1/12. I'm glad for that. It makes my whole day. All right, well, that was a lot of fun for nobody here but me. Is maintained because of the gravitational attraction on the mass of the star being pulled inwards and this heat pressure. The same thing you learned from chemistry, PV equals nRT, being required to maintain a specific temperature. Now, this isn't going to be part of the equation of what we're doing here, by the way, because this problem is less about this and more about what happens when the star's internal temperature heats up. Because when a star's internal temperature heats up, by definition, the star is going to have to start to expand. You see, the fusion process that the star uses is relatively stable as long as all you're fusing is hydrogen into helium. But the helium is dense and goes to the center of the star, and the hydrogen stays on the outside. But then you get enough pressure, the helium can start fusing. It's going to start making lithiums, nitrogens. They're all more dense than the lithium, so they float to the center. And then, of course, the carbons start fusing with stuff, start making bigger things too. I mean, your star ends up being a shell, a bunch of concentric shells, like those little dolls you see, where one doll fits inside the other. That's really what a star becomes, with the lighter gases on the outside and the heavier elements on the inside. And your star will continue to do that until it starts to fuse iron. Iron's the breaking point. When iron is starting to form on the center of the sun and it gets hot enough, when the iron starts to form, the process becomes less efficient. So during this process, the star is ramping up and getting hotter and expanding outwards and expanding outwards. And as it does, it has to cool because of PV equals nRT. Once it expands too far, the volume gets too big, the pressure in the star goes down, there's not enough force to allow those fusion processes to happen. Temperature starts to drop, which is why it got bigger but started to turn red giant. And then the star begins to collapse on itself. When it starts to collapse on itself, bad things are going to happen. Bad things are going to happen. If it's a pretty small star, it'll just kind of burn out. If it's a little bit bigger than ours, it'll go white dwarf, which means new fusion, a lot of it, of heavy stuff, things bigger than iron. And it'll burn bright for a couple of years, but that star's on its last legs. If it's bigger than that, that's when the wicked stuff starts to happen. That's when things start to break in physics. When you go past white dwarf, it collapses even further, and you can start to get the beginnings of a supernova event, which we might actually get to witness in your lifetime in the night sky over the next couple of years, as one of the stars in Orion has suddenly started to change its brightness over the last couple of years, and scientists believe it might be collapsing into a supernova explosion. Should we get a supernova explosion in that star, it will be brighter than the moon for a couple of months. Yeah, it'll be pretty wicked. So it's a relatively close star too. So the remnants after a supernova explosion can be a neutron star. And neutron stars are interesting because they violate the Pauli exclusion principle. But that's what we're talking about here. And I'm not going to talk about the Pauli exclusion principle because that's where I would ask you guys if you remember anything from chemistry, to which you'll say, nope. And then I'll ask the AP kids, come on, you remember the Pauli exclusion principle? And they'll say, nope. And then somebody's alarm will go off and I'll be frustrated. So, a star with mass m and radius r, like our sun, rotates once every 31 days. After undergoing a gravitational collapse, the star forms a pulsar that is observed by astronomers to emit radio pulses every 0.1 seconds. By treating the neutron star as a solid sphere, deduce its radius. So, let's do it. The star begins big. And it's rotating, as they say, once every 31 days. So that they're telling me omega, once every 31 days, is 2 pi every 31 days. You're probably going to need that in radians per second. I'll leave that to you because I'm not actually going to do this problem. I'm just going to set it up for you. Now, when the star collapses, it becomes much smaller, but it retains its mass. Now, it really doesn't. A neutron star might, under best circumstances, retain 80 or 90% of its mass, but usually it ejects tons of mass into the surrounding space. But let's assume, like they say, that it stays the same mass. If I remember correctly, moment of inertia for a solid sphere is 2/5 mr squared. And I do remember correctly. And if there's no external force acting on the system, the angular momentum before is going to have to equal the angular momentum after. So, I omega before has to equal I omega after, which means 2/5 m r before squared times omega before has to equal 2/5 m r after squared times omega after. I'm going to notice that it really doesn't matter what shape this is, apparently. All that matters is that it's related to the radius. So we want the after radius, RA, which is going to be equal to the square root of omega B divided by omega A times R before. So this is omega before. They gave us omega after. In my problem, they tell me that the pulses are every 0.1 seconds. Now, here's the problem. They don't emit radio pulses 1 pulse per rotation. That's incorrect. The problem should state they release 2 pulses per rotation because they're not pulses at all. A neutron star spins so fast that radiation is given off at both poles of rotation. It's like a lighthouse beacon. The worst thing is the pulsar spin is separate from the actual spin of the star. It's a secondary spin speed. You see, it's spinning this way, but the pulses of light are being given off along the poles, which they themselves are also spinning, because it's spinning 2 different ways. So we're getting the pulsation spin rate, which is not related to this spin speed, but this problem conflates the two and suggests they're the same. The problem is wrong, but you have no choice but to do it this way. But I'd hate for you to leave if you're not understanding your astronomy, since you don't remember your chemistry. So we're going to go with this because this is what they want us to do, but it's not really how it works in a neutron star. By the way, I'm done. It's 2 pi over 0.001. You need to convert this to seconds, substitute it all in, you'll get your answer. But like I said, basing on the pulses is the wrong thing to do. By the way, if the star does explode at a full supernova, it ejects all that stuff out into space, all that stuff still has an angular momentum. And it's going to be huge ejections of iron and heavier elements and lighter elements. The lighter elements fly farther because they have less mass. The heavier elements don't fly as far because they have more mass. Which makes you wonder, or maybe not wonder, why all the inner planets are rocky and iron, Earth, Venus, Mars, Mercury, and all the outer planets are gaseous, made of mostly hydrogen and helium. Maybe it doesn't make you wonder. It should make you think that what was here before was a bigger star that went supernova. And what coalesced afterwards was a star and a bunch of rocky planets that had been ejected from that supernova. Had to be. And we already know what direction that star had to be spinning because our planet revolves around the sun in that same direction because momentum had to be conserved. So the momentum of the solar system is also conserved and matches the momentum of the star that was here before. It's nice to know things.